Alrighty, and hello Jessica, who's watching this somewhere. Maybe because I'm just putting off a MATLAB discussion forever and forever, but bless you. But again, considering that the spectra of 771 is hovering over half a class, it's probably best to put off like really digging into the homework anyway. So figured about half of you would appreciate that. So really by the time I finish covering this week's stuff, then it'll be possible to do really the first two homeworks. Okay, check that. Which really is 5 out of the 7 problems that we have all semester long. Okay. So, new chapter. This board is healthy. I don't think this is helping. Oh, yeah, that's even worse. Okay. All right, so now that there's no hope. All right, spectral methods. So given that most of our research program is about a spectral method, certainly this is my favorite part of the class. And really the first time I took a numerical PDEs class, well, just like all 3 of you, was in my first year as a graduate student also. And just like this class, the focus is mainly on finite difference, but some time was spent on spectral methods. But during that small part, I was like, oh, this is nice. And the rest was history. Now, so I'm going to start with comparison of properties of finite difference versus spectral methods. Now, the key comparison, the key contrast between them is in the accuracy. So with finite difference methods, what we've seen is that the error is of order h to the p for some p. So you have some grid with spacing h. So you replace your derivatives by these finite difference formulas, and all of those have an error that's some power of h. We usually saw h squared, like for a center difference. Now, what we have in the case of spectral methods is that the error is of order h to the 1 over h. Now, because we have h in both the base and the exponent, that represents a more rapid degree of convergence. So to explain why, as h is going to 0, then the exponent, what's happening to the exponent?
As h goes to 0?
Yeah.
The exponent gets bigger.
Yeah, the exponent is going to infinity. So what's happening is, now here as h is getting smaller, the exponent is fixed. Here the exponent is getting larger. So we already know that as the exponent increases, like if you change a second order method, swap it out for a fourth order method, then h to the p raising h to that larger power is going to give you something smaller and smaller. So here it's automatically getting smaller and smaller at a faster rate. So another way of putting it is, so this is less or equal to some constant times h to the p for any p. So this is also referred to as superconvergence, or also exponential convergence. So the order is exponential, just because it's going to zero. The error is going to zero at a faster rate than h to any fixed power. Just because the smaller h gets, the larger the exponent. Okay. Now, I think, well, if spectral methods are so accurate, why do anything else? Well, unfortunately, there is a legitimate answer to that. So the thing about spectral methods is, compared to other methods like finite difference and other ones that we could talk about like finite element, finite volume, etc., spectral methods are only applicable to a rather narrow category of problems. So first, problems that have smooth solutions. That's the only situation in which you see this kind of superconvergence. If the solution is not smooth, so there's a discontinuity somewhere, like in the solution itself, or in a derivative, like it has a kink in it, then it reverts to this kind of convergence. The same you get in finite difference methods. But there are important problems that have smooth solutions. Heat equation, for instance. Solutions of a heat equation are infinitely smooth. Okay. Now, the another limitation is that.
Wait, so what is the limitation?
In other words, when I say limitation, spectral methods are limited to problems that have these properties.
Okay.
Sorry about that. I should make that more clear. So, okay. So, okay. Now, what do I mean by nice domain? Certainly, the rectangles or whatever box and however many dimensions. Also, circles, spheres, etc. Because in spectral methods, you're trying to express the solution in terms of some basis functions that have certain nice properties. And you tend to only have those on these nice domains. And with simple boundary conditions, for example, periodic or homogeneous boundary conditions. Okay. Now, one more limitation. So the conventional wisdom is that, in addition to these limitations on spectral methods, they're meant for problems that have constant coefficients, especially on the rectangular domains. because of nice properties that Fourier transforms as they relate to derivatives, and like sines and cosines, since the derivatives have such a simple form. And if you have a constant coefficient, then you get to keep that advantage. Fortunately, this one, as I said, is conventional wisdom, and it is debunked by me. So, okay, that sounds horribly immodest, but I really don't care. So, you got me full professor, so whatever. Really, ever since I discovered spectral methods way back in 1992 and learned about these nice properties they have and these limitations that they have, it really, honestly, just kind of pissed me off. Because here's a way that we can solve PDEs, certain PDEs anyway, with an order of magnitude better, more effectively in terms of accuracy, efficiency, and so forth, but only for this very narrow category of problems. I thought, well, I don't think it should be that way, especially for linear PDEs. So here we're talking about even a small subset of those, because solutions of linear PDEs, whether it's something in this nice category or outside of it, they tend to have similar behavior. It's just that when it comes to properties of other PDEs, in terms of eigenvalues, eigenfunctions, etc., there's very little known about them. So that's why spectral methods haven't really broken out of this category. So as a first-year graduate student, I thought, well, I want to do something about that. And at least for these three things, I was able to make progress on this one. That you can realize the same superconvergence and also higher accuracy in time with even with variable coefficient problems. And in fact, it's really the last paper I published that probably got me full professor, where there was actually a proof of this for parabolic PDE. The first one might be making progress on that one too. Like my summer work at NRL dealt with some problems that definitely do not have smooth solutions. The solutions themselves have discontinuities, but the results I got were still very promising in terms of higher accuracy. I haven't really been able to fully analyze that yet. Maybe next summer, to see what can be done about this one. This one, much, much, much harder nut to crack. Although the dissertation topic that Vivian has taken on is going to be an attempt to do something in that direction. But I think it's something that's a long-term thing. So that means I gotta hang around here for the next 20 years or so. Well, have my career go that long. I'm not saying it'll necessarily be here, but we'll see. Okay, so, and the thing is, now, why is it that I should latch on to what seems like a rather esoteric goal like that, to make some category of methods, and of many numerical methods of PDEs, become more applicable beyond its normal sphere? What difference does it make? And the answer is if successful, it can make a huge difference, because, and that's what attracted me to it in the first place, that it can result in solving these problems that are solved all over the place in your research labs, industry, etc., at great computational expense. That when I say it can solve it faster, it's not just a matter of solving like twice as fast or even 10 times as fast, but a whole lot faster than that, hundreds, thousands of times. If that part of someone's job of running some simulation, then waiting for the results, and then doing something with those results, if that part of their workday is cut to a fraction of the time that it took before. And that changes how effectively they can do the rest of their job. It gives them more time to do the rest of their job. The simulations that can be run, more of them can be run to work with the data that they have more effectively. Oil companies, for instance, their simulations take months, so they may have a large number of models for their reservoir, but maybe you only have time to run the simulation on one of them. And what if that one is an outlier? If they could run more, if they had time to run more, that would be a game changer for them. So that's really what I was looking for and what I stumbled into as a first-year graduate student. Well, this is my game changer. So, and that's hopefully something that budding mathematicians in general try to see. What is their game changer? Okay, so we'll see what goes in my tombstone over this. But okay, so that's my soapbox time about spectral methods. So now to actually learn something about them. Okay. I recall in my class, the class was taught by my first advisor, Joe Oliger, and he didn't really have anything to say in class about spectral methods. I just read it in his book. But however you get the info, I guess. Okay. Now, in this chapter, I'm going to cover two types of spectral methods. First, if we have periodic boundary conditions, then that calls for representing your solution using a Fourier series. So your solution, if we're in one dimension, is going to be some linear combination of these functions, e to the I kx, if you're on the interval 0 to 2 pi, because the functions e to the I kx, those are cosines and sines, they're 2 pi periodic. Okay. All right. And that's probably the only one I'll be able to talk about today, especially after my endless rant. But the other kind is if you do not have periodic boundary conditions, instead of these Fourier basis functions of e to the I kx, use Chebyshev polynomials, which I just covered in 460. These polynomials are defined in the interval -1 to 1, so we can always scale the problem to that interval and use them that way. So Chebyshev polynomials also have a lot of nice properties. Taking their derivatives is not so simple as it is with these. And actually, this is something that I've wanted to branch out into as well. Like my work is focused on this case, but it'd be nice to generalize to this to handle a wider variety of boundary conditions and more effectively. Okay. Now, so how we, let me show you how we approximate derivatives in a spectral method. It's very different from finite difference. So before I get into the equations, I'll give the main contrast between finite difference and spectral. So finite difference methods are local, meaning that derivatives, whatever derivative you want to approximate at whatever point, is approximated by some combination, will be a linear combination of values of your function u of x only at points near xj. Like for instance, with center difference, we used u of xj and u of xj plus h and minus h. So only 3 points altogether. So we refer to that as a local approximation. Which makes perfect sense because a derivative is defined in terms of a limit. Like limit of f of x plus h minus f of x over h. So it uses, so information about the function near that point is enough to approximate the derivative. Whereas spectral methods are global. Use all the points. And that's what actually leads to that order of accuracy, that superconvergence. Okay. Now, I'm going to establish some notation here. All right, so Fourier series. So the exact Fourier series of f is going to have infinite sum of so these Fourier coefficients times your Fourier basis functions. And the true Fourier coefficients are defined as an integral Now, we, however, are going to be working with an approximation of u. So certainly we can't work with infinitely many coefficients. We have to truncate this at some point. So we have so we call this the, instead of a Fourier series, it's the Fourier interpolation. So elsewhere, you're familiar with polynomial interpolation. This is a different form of interpolation, but the idea is you're matching u at selected points, equally spaced points. So uj, which is an approximation of u of xj. So it has this formula, but it's going to be similar to the other. Actually, it's exactly this one, except we are truncating the series to n terms. Okay. Our grid points, yes, xj, oh, sorry, it should be xj right here. So we're evaluating the series at a particular point, xj. So this is going to be 2 pi over n. And we assume that n is even. Thus, the n over 2 here. J goes from 1 to n. So we're on the interval 0 to 2 pi. Notice 0 is not included as one of the grid points, but 2 pi is. So when you have periodic boundary conditions and you have your grid on your interval 0 to 2 pi, you leave out one of the boundary points, you include the other one. You only need one because it's periodic. So we may not have 0 on our grid, but we know the value of u at 0 because it's equal to the value at 2 pi. Different books will leave out one boundary point or the other. Okay. Now, these coefficients, instead of defining as an integral, we want to work with the, so this is a discrete version of a Fourier series. So that's going to be h times the sum, and minus ik xj uj. Actually, I should say not even approximately equals. It is exactly equal at those points. It's just an approximation of u elsewhere. Okay. So these coefficients are chosen so that this interpolant will exactly match u at least at those endpoints. Now, I'm using the subscript k u hat sub k to refer to the approximate Fourier series coefficients, whereas over here, I'm using u hat of k if it's a function to refer to the true Fourier coefficients. So this is an approximation of that. Can anyone tell me, how does this relate to that? Like, what kind of approximation is this of that? Yeah, like, if the true coefficient is an integral, in what way does this approximate that integral? What kind of sum? What do we call that?
Sorry, a harmonic?
No. What?
Riemann.
Riemann, yes. You're searching for the right R word.
It was like RI something.
Yes. Yeah, this is a Riemann sum. Riemann was such a tragic figure. He developed so many things, and so many things named after him. Unfortunately, he died at the age of 40 of tuberculosis shortly after getting married. So,
Was he French?
probably?
Yeah.
I'm not sure. Okay. I gotta find out. German.
Oh.
Okay. Yeah, he died in 1866. Okay. Although there was really a tragic case of a young mathematician. The mathematician dying young was Galois, who a branch of algebra, Galois theory, was named after him. He died at the age of 21 in a duel. Yeah. Yes. And apparently he was trying to write things down frantically because he knew he wasn't going to survive the duel and made sure that things were left behind. But yeah, but in some schools, I remember Purdue, there was a whole course on Galois theory. Yeah, but there are certain books you can find that have all the tragic tales of mathematicians and the scandals and so forth. It's made quite a movie. I mean, maybe that's the way to make math interesting to people. Just put the stories out there. Okay. All right. So now the interesting thing about these coefficients. All right, so we have n coefficients. K is running over these endpoints. I chose these. The reason we use these limits, minus n over 2 plus 1 n over 2, because we have to have n coefficients altogether, is so that it's as symmetric as possible. So it's roughly centered around 0. Now, here we have n coefficients to compute, and each one requires n terms. So you might think, oh, that's going to take on the order of n squared operations to compute all of these coefficients. But we don't need to do that. We can do this in n log n operations using the FFT, fast Fourier transform, which was named one of the top 10 algorithms of the 20th century. Okay. So the idea is we want to use all the grid points to approximate u prime of x by computing the derivative not of u, but of this function p of x. P of x is just the truncated Fourier series taken as a function of x. And this is called, since it's a truncated Fourier series, but it's also the Fourier interpolant, it's also called the BLI, which stands for band limited interpolant. Of course, Bill, you recognize that term from one of my papers. It's called band limited because instead of taking k from minus infinity to infinity, we're truncating it to a certain range of coefficients. So frequencies, so these k's, this e to the I kx, k is a frequency. So we're limiting our function u of x to a band of n frequencies. Okay. So the idea is we can compute the derivative of this exactly, and then take that as our approximation of a derivative of u. But we want to compute this derivative, the derivative of this, in terms of the values of u, not u hat. So ultimately, that's what we're going to arrive at.
What's the fraction for k for the lower bound?
Oh, that's a
Minus n over 2.
minus n over 2.
Oh, okay.
Yeah.
Sorry.
Now this board is. Okay. Now, actually, I wonder if there's a better way to do this when I have my notes. But that's probably going to lead to disaster if I go off script. Again. So, what I'm going to do is I'm going to find this function, delta j be equal to 1 if j is equal to 0 mod n. So if j is an integer multiple of n, the number of grid points, then it'll be 1 and 0 otherwise. Okay. And this is called the discrete delta function. And I mentioned its continuous counterpart several classes ago, the Dirac delta function, really the distribution that one of the professors described by linking it to Voom. The function that's 0 everywhere except at one point. Okay. Now, how this helps me is that I can write uj in terms of all the values of u. So I can write it as uj is a combination of all the u values, where what I'm combining them with is the delta function, because the delta function is always 0, except when m is equal to j. So that's a way of picking out that correct u value. Okay. So that means I can express my band-limited interpolance as a sum of a similar form. So I'm going to have um, and then I'll have pj of x minus xm, where this pj is the band-limited interpolance of this, of delta delta j. Yeah. Okay. So just as this represents the true discrete delta function, here we have an interpolant of that same delta function. So this function, delta j, is going to be equal to 1 at when its argument is 0. So in this case, it'd be at xm. Or, do I have this written right? Okay, yeah, so if I plug in xj here, and therefore xj here, this will be 0 except when m equals j, which is what I want. All right. Okay. So now, suppose I take a derivative of both sides of this. Okay. Right. Well, what I want is this, but I'm going to approximate it by p prime at xj. And for that, I'm going to take a derivative of this and plug in xj. So I have um, and I have pj prime xj minus xn.
Does the BLI of delta J have to be xj minus xn, or is it just here?
Oh, okay. All right, so what's happening here is we're only taking the BLI of this one function, and it's just that every time this function appears in the sum, we're supplying different arguments to it.
Okay, so that's kind of like an arbitrary x.
Yeah, this x is arbitrary. Okay. All right. Now, this is the form of the approximation I'm looking for. Because even in finite difference methods, we wanted a derivative at some grid point to be a linear combination of values of u at other grid points, or that grid point itself. So here we have the exact same thing. So these are the coefficients in our stencil. And I don't know if I mentioned this, actually I'm not sure if I mentioned it at all, or certainly enough. We're talking about finite difference methods. When you describe a finite difference formula, so this derivative is equal to this combination of u values, that combination is called a stencil. And in finite difference methods, a stencil will only consist of a few points, like forward difference, backward difference, center difference, etc. Here, exact same idea. We're expressing a derivative as a linear combination of values of your function. So this again is a stencil, and these values here are the coefficients in that stencil. The difference between what we have here now and finite difference methods is that these coefficients will generally be non-zero for all points, whereas in finite difference stencils, these are only non-zero at a very few points. Okay, so now the focus shifts to computing these. Once we have these, we have our differentiation formula. Okay, so if we look at the Fourier coefficients for the delta function. Now, by the definition, it's that Riemann sum we saw earlier. And what I have here is e to the minus I k xj times delta j. But now I can evaluate this because this is 0, except when j is equal to 0. So something seems off here. Okay. All right. Because xj is equal to j times h. So if I plug in j equals 0 here, then I'm going to have e to the minus ik0, which is 1. So everything is going to go away, except I'm going to have, oh, wait, Sorry, I goofed. That shouldn't be here. I scrolled down to the wrong formula. Okay. There is a factor of h here. That's what's supposed to be here. Okay. Now, okay. So if this is equal to 0, except when j is equal to 0, what should this simplify to? Yes, because when j is 0, I have e to the 0, which is 1. The h is the only thing that survives. So I'm plugging in x equals 0 here. So what that means is every Fourier coefficient is the same. It's equal to h, which is unusual. Normally when you compute Fourier series coefficients, as you go to higher frequencies, they go to 0, they decay. But not with a function like this that is 0 everywhere and has a sharp spike at one point. When you have a function like that, its Fourier series coefficients do not decay to 0. Here they all have the same value. Okay. So, my function, my band-limited interpolation of the delta function, and everything that I wrote up here by mistake, I now have to write correctly down here. Oh my god. I screwed up everything. Yeah, I literally screwed up everything in this formula. Now my eyes kept wanting to go down to the next formula. Okay. Sorry. I'm a real screw up today.
Wait, what did you change? Just the bounds on the summation?
Yes. Yeah, so when we're going from function of x to Fourier series coefficients, it's got to be a sum over j. Going the other way around, Fourier series coefficients to function of x, it's these coefficients. Here we have from function of x to Fourier series, it's a minus. Here it's not a minus. That's the only thing I wrote correctly in the whole thing. Dang it. E to the I, k, x times delta k hat. Okay. So transform, inverse transform. All right, and that's why the sum over j, that's why all the terms in this went away, except when j equals 0. Is there any lingering confusion from my many mistakes? Okay.
But which one is the transform and which one is the inverse?
Inverse.
That's
Yeah, transforms when you get the Fourier series coefficients.
okay.
Inverse when you go back to function of x.
Got it.
Okay. Now, so now what I can do is, well, now I know what this is. This is h. So I'll just fill that in. E to the I, k, x is the only thing left in the summation. So this is a function that is equal to 1 when x is 0, because if I plug in x equals 0 here, I'm going to have all my terms be equal to 1. I have n terms, so I'm going to have hn over 2 pi. But h is equal to 2 pi over n.
Does it say x minus 0?
X equals 0. So if I take this and plug in x equals 0, I get h over 2 pi times n, because I'm adding up 1 n times. And this all simplifies to 1. Whereas if I plug in any of the other grid points, so x1, x2, etc., I'll get 0.
So you get 1 or 0?
Yeah, on the grid anyway. So I should mention that the true delta function would behave like this. It's equal to 1 here at this one point. I don't have colored chalk to show this, but it's 1 at this one point and it's 0 everywhere else. Whereas the BLI, band limited turbulence, will not behave exactly like that. It will be 1 here, and at equally spaced grid points, it will be 0, but there's going to be oscillation in between. Because it's only an approximation. In fact, there'll probably be some nasty high-frequency oscillations in here because of this terrible discontinuity here. That spike is bad for Fourier series. Okay. So really, all I have to do is take the derivative of this and plug in x equal, I'd be plugging this in, and that would get me all of my coefficients. So, but the problem is, if I were to take the derivative of this with respect to x, well actually, what is the derivative of this with respect to x? There's only one part of it that would change.
Just be ik times e to the ik.
Yeah, we get a factor of ik down here. You think, oh, well, we just use that and use that in here. But here's a problem with that. I need n of these coefficients. And if I go ahead and just do what you just described, I have each one of those n coefficients described by a summation consisting of n terms. So it takes me n squared terms to describe all my coefficients. So this form is too cumbersome for this. What I need to do is, if I'm going to take a derivative of this, I want to be able to express this using one expression, one term. In other words, what's called, I need this in what's called closed form. In other words, not involving a summation. I want to condense this to a single term expression. Then I can take the derivative of that and plug in xj minus xm. Then I'll have just one formula, one concise formula for all my coefficients. So it's getting that in closed form where things get kind of ugly. As if they haven't been ugly already. Okay. Okay. Yes. Trig alert. Sorry, I couldn't resist. So this sum.
Now I can't spell morning.
What? Okay. Okay, so I have, so I'm just focusing on summation now, forgetting about the h over 2 pi part, we'll put that back in later. E to the I kx. Now, this is equal to, so I can use the definition of e to the I kx, breaks up into real imaginary parts. Cosine kx plus I sine kx. Now, the nice thing is, this function is pj of x. It's a real valued function. So, we should only need to take the real part of this. So this here is 0. So we're just going to forget about that and focus on the cosine part. Now, I don't have this worked out in the notes, but I'll work it out here because I did it on paper earlier. So it should all work out. Excuse me. So this sum of cosine kx, I'm going to multiply and divide by sine of x over 2. So I have a multiply in here inside the sum, and I'll divide by it outside the sum. Okay. So then on the expression inside the sum, I'm going to use a trig identity called a product to sum formula. So that's going to be 1/2 sine of, actually I'm going to write it this way for convenience, minus sine of this minus this. So that's going to be k minus 1/2 x plus sine of these two arguments added. So it's going to be k plus 1/2 x. So then what I'm going to do is write out, so we'll forget about this focus on the sum. I'm going to write these out from k equals minus n over 2 plus 1 up to n over 2. So starting with the lowest index, so all terms will have a 1/2. So I'll just pull that out. So I'm going to have minus sine. So here I'm going to set k equal to minus n over 2 plus 1. So that's going to give me minus n over 2 plus 1/2 x. Okay. Because I have plus 1 and minus 1/2, giving me a plus 1/2 overall. And then over here in I'm going to have sine. So k is the minus n over 2 plus 1 plus a half. So that's minus n over 2 plus 3 halves x. So that's the first term in the sum. I won't do very many. I do want to do the second term. So k will be minus n over 2 plus 2. So I'll have minus sine. So minus n over 2 plus 2 minus a half. So that's minus n over 2 plus 3 halves x. And then I'll have plus sine of, so minus n over 2 plus 2 plus a half. So minus n over 2 plus 5 halves x. And then the merciful dot, dot, dot. So then I'll jump directly to the last term when k is equal to n over 2. So I'm going to have minus sine n over 2 minus a half x plus sine n over 2 plus a half x. Close.
What's positive n over 2?
Here, yes, because of plugging in the upper limit. Okay. I probably should have written out more terms to make it clear, but it's Monday and we're all brain fried. But I've written enough so that you can see in there something that can be simplified.
Well, those cancel each other out.
Which ones?
The n over 2 plus 3 halves.
Yes, these terms cancel out. This is the second part from the first term, and then the first part of the second term. And what will happen is, actually, well, based on that, even though I didn't write out more, what do you think is going to happen?
You just have the first term and the last term.
Yeah.
Just like, yeah, in summation.
What kind of a sum is that? What do we call that?
It's the one that's like add the first 100 things together, right? No, you like have figures.
Is that
no.
Fibonacci?
No. Starts with a T. Comes up in Cal 3. Telescoping. Yes, telescoping series. What? Okay.
Now I know.
All right. Yeah, like a practical telescope. Yeah. So yeah, really everything will go away except these two terms. So now, this is what I mean by closed form. The number of terms is no longer dependent on capital N. It's just two terms. And in fact, I'm going to go further. I want to condense this down to one term. But before I do, I'm going to mess with this a little bit. Sine is an odd function. So if I change the sign of the argument, it changes the sign, S-I-G-N, of the value. So negating this negates this. So what I can do is I can change these signs and put a plus out there. Now I can use another trig identity. So this is I used a product to sum identity earlier. Now this is the other way, a sum to product. So this trig identity is sine A plus sine B is equal to 2 sine A plus B over 2 times cosine A minus B over 2. And here I have a sum of sines after rewriting that first one. So now I can say that the summation well, the 2 is going to cancel with a 1/2 that I had earlier. So now I'm going to have sine of, okay, so since this whole thing turned out to be 1/2 sine n minus 1 over 2x plus sine n plus 1 over 2x. Okay. So the 2 cancels with 1/2, and what I'll get is I'll add these together, and that'll give me, well, it's their average. N minus 1 and n plus 1 over 2. The average is going to be n over 2, so I'll get nx over 2. And then I'll have cosine. So if I take the difference of these, and it really doesn't matter the order in which I subtract them, because I'm taking cosine of that anyway. Cosine is an even function. So the difference of these would give you just x over 2, because the n over 2's will cancel. Okay. Now, so now what I can do is, now that I have that sum boiled down to just one term, I can conclude that Pj of x is equal to h over 2 pi, I dropped that earlier, and then I have sine nx over 2 times cosine x over 2, and I was dividing by sine x over 2 before. So I can write this as h over 2 pi, and then sine over cosine is what? Sine over cosine. What? Yes. So I'll tangent in the denominator because it's okay. And then here I have sine nx over 2, but I'm going to write that as, keep in mind that n is equal to 2 pi over h. So n over 2 is going to be just pi over h. So I can have sine pi x over h. Okay. All right. So this is my band-limited interpolant of a delta function, a function that's equal to 1 at x equals 0, and it's equal to 0 at all the other grid points. And because sine is an oscillatory function, that's what leads, I'd drawn a graph earlier of a BLI, and it was oscillating a little bit, prove those points were at 0, so that you can see that from here, that's going to happen. Okay. Now, but what I need to do now is take the derivative of this, and then substitute in xj minus xm. So pj prime of x. So I'll take the derivative of this the normal way, quotient rule, yay. So, okay, so I'll have tangent times derivative of sine, so it's cosine pi x over h times pi over h, and then minus sine pi x over h times the derivative of tangent. What's the derivative of tangent? Oh, you're thinking of the integral of arctangent, derivative of arctangent. It's 1 over 1 plus x squared. Okay. So it's secant squared. Okay. All right. Well, fortunately, you don't have to know that for next semester because you're teaching 102. So, and then chain rule, we get to 1/2 all over tangent squared of x over 2. Okay. Now, so now what I'm going to do is, what happens if I plug in just some grid point into here? So pj prime at xk, so that xk is equal to k times h. So if I take that into account, so I'm going to have tangent kh over 2, cosine of x is kh, so the h's will cancel and I'll get pi k, minus sine, again pi k, and then secant squared kh over 2 times 1/2 all over tangent squared kh over 2. Okay. Can anyone tell me how this simplifies?
Can you rewrite secant as can't rewrite secant.
Okay, so simplification does not lie in secant. Focus on the sine and cosine. Keep in mind k is an integer.
So if we replace k with 1,
For example, yeah.
so
Well, it's a factor of pi.
Yeah, so sine or cosine of a multiple of pi is
Right.
what?
Well, 1 and 0.
Okay, which is which?
Cosine 1 and sine 0.
Sine is 0, so yeah, this whole term goes away.
and cosine is negative.
You're both right. It's plus or minus 1, depending on whether k is odd or even. So it's 1 when k is even, and minus 1 when k is odd. Okay, so we're going to write down the simplified form.
Oh, I'm just trying to remember. What do we need PJ prime for?
Coefficients of our stencil.
Okay.
Yeah. And
So I'm getting,
I'll be getting there very soon.
okay.
Okay. I know, such a long, winding, torturous journey. Well, our suffering ends in 13 minutes. So, okay. So PJ prime at xk reduces to, okay, so there's, h over 2 pi minus 1 to the k. That's what happens to the cosine. So that's an easy way to express cosine of k pi, where k is an integer. And then we have tangent in the numerator, tangent squared at the same angle in the denominator, so we'll just simplify that. So we have tangent kh over 2 in the denominator, but I'm going to write that as, oh wait, I forgot something. Oh, dang it. Okay, the last line down here, pi over h. So that should have come on down. So that should be up here also. Okay. Oh, what? Yeah, I had this, and I forgot to bring it down.
Okay.
Okay, that was a priceless look. Okay, now, so now Jessica can see everything of importance. But now the pi's will cancel and the h's will cancel. So we're left with 1/2 minus 1 to the k, and I'll bring a tangent up to the numerator. That's cotangent of kh over 2. So that whole mess of the derivative of the interpolant of the delta function boiled down to this. And probably never would have expected that cotangent of all things would appear. Okay. So now if I return to the derivative that we want, u prime at xj, which is approximately, approximated by this sum of pj make sure I write it the same way. Okay. Pj prime at xj minus xm. Okay. But that is equal to the sum of um. So here, in place of, because this is just equal to j minus m times h. So now I can fill that in here. So it's going to be 1/2 minus 1 to the j minus m cotangent of j minus m h over 2. So these are the coefficients of your stencil. So that's how you linearly combine all the values of u to approximate its derivative. Okay. Excuse me. Now, one thing we're pointing out is as n goes to infinity, the number of grid points, which also means that h is going to 0. Well, cotangent is cosine over sine. Now, cosine, as h goes to 0, that's going to go to 1. Sine, for small arguments, sine x for small arguments, small x, is essentially x. So u prime converges to, so we have this sum, m equals 1 to infinity, of um. And so really what I'd be doing is cotangent of this converges to just 1 over this. So I'm going to have minus 1 to the j minus m over j minus m. Because I'll flip this, the 2's will cancel. Oh, and then that goes in the denominator. So for particularly large values of n, the coefficients look like that. Okay. Now, back to the finite case. If I want to write this in matrix vector form, so u prime of x1, u prime of x2, down to u prime of xn, I can write this as a matrix times my u values, u1, u2, down to un. And notice the entries of my matrix are right here. J is a row index. M is a column index. But notice that the formula does not depend just on J or M individually. It only depends on the spacing, J minus M. So, as a result, this matrix, all the entries down any particular diagonal will be the same. So we're actually going to have, something seems off here because when k is equal to 0, cotangent of 0 is cosine over sine. That's undefined. Okay, so I'm not sure why it was not taken into account in the notes, but all right, that's something else to look at. But down the diagonal, it's going to be zeros. Now, well, actually, okay. So if I look at Pj prime here at x naught, oh, okay. Sorry, this is bugging me here. So if I go back over here, where as x is going to 0, like here, as x is going to 0, I'm getting 1. But as x is going to 0 in the derivative, okay, well, secant is going to 1. Cosine is also going to 1. So I can forget about those. And then I have the tangent over tangent part is bugging me. That's something I have to think about more. But however, what I can believe is that the way the band-limited turbulent delta function acts, like there's supposed to be 1 here and 0 at these other points, but it does so in a way that it's a horizontal tangent, and I'm pretty sure it is how it behaves. Thus, the derivative should be 0 at that point, which would mean 0's down here. But my notes are letting me down, and that's my fault because I wrote them. But on the off diagonals, we have this expression here. So, for example, when j minus m is equal to when j minus m is equal to 1, so on this right above, I'm going to have 1/2 cotangent h over 2, and then on the other side, right below, it's going to be minus 1/2 cotangent h over 2. When you negate this, it negates cotangent. So on one side diagonal or the other, this will be the same no matter what. This just depends whether the difference is odd or even. But this will be opposite signs on opposite diagonals. On the next diagonal up above, you'd have minus 1/2 cotangent 2h over 2. And then down here, it will be plus 1/2 cotangent 2h over 2. And then as you go up further diagonals, you have increasing arguments, 3h over 2, 4h over 2, etc. And also alternating signs. The matrix is actually skew symmetric. In other words, it's equal to the negative of its own transpose. First derivative is naturally skew self-adjoint operator, so its approximation should be a skew symmetric matrix. Like, for instance, the center difference matrix for first derivative does in fact have that property. I'm out of time, but there's formulas in the notes for if you did the same thing but with taking a second derivative instead of a first, what the matrix is for that, which involves actually cosecant squared, which, by the way, is a derivative of cotangent, coincidentally. So in fact, except for the diagonal, you can take derivatives of these entries. Now this matrix, where every entry along the diagonal is the same, so it behaves to like this. I have mentioned such a matrix before. Like, what is that called? We have a matrix that has that behavior.
What kind of behavior?
Where if you look along any diagonal, all the entries are the same. Starts with T.
Triangular?
No. I figure someone's going to guess that, but yeah. Toplets. The Toplets matrix. Toplets matrix is nice because we know something about their eigenvalues and eigenvectors. Okay, so that's how we handle periodic boundary conditions. And because we're using so many points, the accuracy is order h to the n, but n is proportional to 1 over h, so it's h to the 1 over. So the error, order h to the n, that's n is 2 pi over h. So it's like that. Unfortunately, I had some other things for Fourier series, but I will deal with that on Wednesday. Okay. Well, to 2/3 of you, good luck of 771.